Okay, as we all know, the sum as n goes from 1 to infinity of 1 over n squared, this right here is equal to pi squared over 6. But have you guys ever thought about, what if we have the sum as n goes from 1 to infinity of 1 over n cubed instead? Oh well, unfortunately, we do not have a nice exact answer for this, but we do know that this right here does converge. So, in this video, I will show you guys how we can do an approximation for a convergent series. And we'll also talk about how good the approximation is by using some integrals. So check this out. And at the end of the video, as a bonus, I will tell you guys the answer to the sum as n goes from 1 to infinity of 1 over n to the fourth power, right? Anyway, here we go. As we can see, this right here has infinite amount of terms. Well, maybe we can just stop at somewhere and talk about the first n's partial sum. And that should be a pretty good approximation, right? So here we go. That's the idea. Let me go ahead and start by saying let s equal to the infinite sum. So we'll just say s is equal to a1, which is the first term that we have, plus a2, plus a3, and so on, so on, so on. And I will write Sn to be the n's partial sum, meaning we have a1 plus a2 plus dot dot dot, but we will have to stop at an. And keep in mind, for the s, of course, this right here is going to include the an right here as well, and then the next term, which is an plus 1, and then the an plus 2, and so on, so on, so on. Now, what we'll do next is, we are going to subtract Sn from s. And when we do that, we see on the left-hand side, we just get s minus Sn. And on the right-hand side, all of these terms cancel, and we have an plus 1 first, right here, right? And then next we have plus an plus 2, and then an plus 3, and then so on, so on, so on. Okay, now, here is the deal. This is our ultimate answer, right? The s, it's an infinite series. That's what we are trying to get first, right? That's our final, the ultimate goal. But we're using partial sum to approximate. When you subtract, the difference is going to represent the remainder. We can also talk about this as the error. So let me write that down right here for you guys. We are going to call this to be Rn, which is the remainder. And imagine if you use the first 10 partial sums for this, then the remainder will be from 1 over 11 to a third power plus 1 over 12 to a third power, and so on. Those things will be the remainder. So that's the remainder right here. And you can also interpret this as the error. If you're trying to get to the infinite series, right, that will be the error, how much you're off by. That's the idea. Now, just like the integral test video, we are going to build a connection between the an's and all that and the integral. To do so, we will use a graph. So here we go. Look at the graph. And of course, you have to satisfy the integral test for the function. And just like the one that we did, f of x, right here, right? This is the graph for that function. You have to make sure this function is positive, continuous, and also decreasing. Okay? And another thing is that, remember, the connection between the function and the sequence is fn is equal to an. So this is the function version and this is the sequence. Now, instead of starting at 1, we are going to be sure we end up with like, an plus 1, an plus 2, and all that. In fact, I would like to just make a mark right here for n, and the next n plus 1, and the next n plus 2, and the next n plus 3, and so on. This is what we do. I want to really get an plus 1. So I'm not going to start at x equal to n. I will actually start right here. When x is n plus 1, I will look at this and then go up, and I will actually make a right end point rectangle. So I will actually go to the left like this, and as you can see, here we have our first rectangle. And now here's the beauty. The base of this rectangle is just 1, but the height is when x is n plus 1, you put n plus 1 into the function, namely you will just get an plus 1. And of course, an plus 1 times the 1, the area right here is just an plus 1 for the area of the first rectangle. Very nice. So right here, let me just keep track. Here is the first area that we have. Now, next, of course, do the same thing. Start at n plus 2 right here, you go up, and then you are going to make a rectangle like this. The base is 1, the height is an plus 2, so the area right here is just an plus 2, okay? And then, of course, we're just going to add up the areas together, so next we have an plus 2, like this. And of course, you can just see that the next one is going to be an plus 3, and then an plus 4, and so on, so on, so on, right? So I'm just going to leave that to you guys. And I'll just put down plus dot 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 like this, okay? Now, of course, this is the moment that we're waiting for, namely the integral. And to come up with the integral, of course, you are going to interpret this as the area under the curve. And remember, for these arguments to work, be sure that the function is positive, continuous, and decreasing so that these rectangles will behave the way that we want it to be. And also, you have to make sure that the S does converge in the first place in order to make sense of this. Otherwise, if you're talking about infinity, who cares about infinity minus infinity, all that? That's impossible, right? Anyway, here's the deal. As we can see, the area under the curve is going to be bigger than the area of the sum of the areas of the rectangles. So if you put down the integral from n, right? This right here is actually n to infinity because we are going all the way, n to infinity, and of course you put down the function dx like this. Well, what's the connection between this and that? Of course, this right here is less than or equal to, because sometimes, just put on the equal to, why not? But in some situations, they may be equal. But anyway, this right here is less than or equal to this improper integral. So this is the idea for that. Now, let's take a look of the other one. Because what if I draw the rectangles the other way? Notice this right here will give us an upper bound, meaning that the biggest error that we can possibly make, right? So let's look at the other version. So here we go. I will still draw the same picture, and I will just put this down right here. So still a f of x and all that. But this time I will just start with n plus 1. Let me just put it down right here. This is n plus 1, and then n plus 2, and then n plus 3, and so on. My n looks like an h, but it's not. Okay, so now, here we go. Draw the rectangles. Start at x equals n plus 1. Go up, but this time, I want the rectangles to be bigger than the area under the curve. So I will just make a left end point like this, stick out like this. And it's pretty much the same idea. The base is 1, and the height is, when x is n plus 1, you put it into the function. Namely, we get an plus 1, and the height times 1 is just an plus 1. That's the area of this rectangle. And then we do the rest. Of course, next one, you just do n plus 2, and then you have this rectangle be sticking out and all that. Okay, so that's the idea. So right here, as we can see, if we add up an plus 1, and the next is an plus 2, and then if you keep on going like this. This time, compare the area of all these rectangles when you add them up, and the area under the curve. As you can see, this will be bigger than the integral from n plus 1 to infinity of the function. And again, this right here is bigger than, and sometimes it can be equal to, because if you have a redundant sequence, maybe they're just exactly the same. But let's just put this down here. So here is the idea. Notice this right here is smaller than this. This right here is bigger than that. In another word, this right here is in between of this and that. So that's pretty much the theorem that I'm proposing for you guys. So let me put this down right here for you guys. Let me put this down right here first. So we have the integral n plus 1 to infinity of the function f of x dx. This right here, which is the middle, and notice this right here, we call that to be Rn. So I will just put this down as Rn and Rn. So this right here is going to be, Rn is in between of these two integrals. So Rn here, and I will put down this right here. The integral n goes from n to infinity f of x dx like this. So this is the bound. Here you have a lower bound, and here you have the upper bound of the remainder or the error that we can possibly make when we use partial sums to estimate an infinite series. So now, let me actually work out an example for you guys. Right here, let me just say I want to use the first 10 partial sums for this. So I will just say, let's say use n is equal to 10. Right? And of course, you can pick whatever n you want. The more the better, of course. When n is equal to 10, if you're talking about this, that means we are looking at 1 over 1 to the third power plus 1 over 2 to the third power plus dot 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 up to 1 over 10 to the third power, isn't it? Yes, it is. This right here is approximately, well, I'll write it down for you, is 1.1975. Of course, you can do this on your calculator with Wolfgang alpha, up to you. So, this is pretty nice. But now, to get a feeling about how good this answer is, we are going to do the integrals business. Now, here we go. I will tell you, this right here is the R10, right? Because the n is equal to 10, so we have R10 in the middle, right here. And again, n is equal to 10. This R10, meaning if you go from 1 over 11 to the third power plus 1 over 12 to the third power, and then just add up all of that, those things is going to be in between of this, which is the integral from 11, because 10 plus 1 is 11, to infinity right here. And the function is, of course, 1 over x to the third power that we are talking about, dx. And then we have the integral from 10, right, because n is 10, to infinity right here, 1 over x to the third power, dx, like this. Right? So that's pretty much the idea. And I'm going to leave these two integrals for you guys to do. I will tell you guys what the answers though. So we get R10. It's in between. Right here, when you work this out, you will get 0.005. And that's the maximum error that you can possibly get. So you can be sure, okay, we are pretty good within 0.005. Distance away from the actual sum. Well, this right here, it's the smallest error that you can possibly make. So I will go interpret this right here for you guys soon as well. Anyway, if you do this on the calculator, just work this out on your own, you get approximately 0.0041 something. Okay? So that's the idea. Now, this right here, it's the maximum error that you can possibly get. So you have a better feeling about how good this is. That's pretty good. So how can we use this though? Well, if today you do 1.1975 and you add it with the smallest error that you are making, you can get a much better idea. Keep in mind, this right here is the smallest error that you are making. So if you go from here and you add this up, you are not making that much of the error. That's the idea of using this. I'm going to leave that to you because I will tell you, note, unfortunately, we cannot have an exact answer for this, but I have Wolfgang alpha. I can do this up to 1,000 or actually 100 billions, whatever I want, right? But I will just write this down. Note, if I do 1 over 1 to the third power plus 1 over 2 to the third power plus dot 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 up to 1 over 1,000 to the third power. Oh, I should have done it over 9,000, but I didn't do it anyway. This right here, let me tell you guys what the answer is. This right here is approximately 1.2020564, and of course more digits after that. So this is the 1,000th partial sum. And perhaps let me just write this down in purple to show you what I mean by using this number here. If you add 0.0041, right? Just do this plus that. This is going to be, okay, let's see. This plus this is 6, this plus is 1, and you carry over becomes 0, and then you put a 2 right here, and then you have the 1. Ooh, take a look. This is going to be 1.2016. So the truth is, when you use the first 10 partial sum, just add it with this, you get really, really good approximation now. If you use this. Very good, right? Because as you can see, if you use 1,000th term right here, you get 1.202. Hey, that takes a lot of time if you do it by hand. You enter this on the calculator or so. Of course, don't use Wolfram Alpha, that's too cheating. But if you are just doing this, then you can see this is a really good approximation on how you can use this right here. The error that you are making already, so just add it to here, so you have much better approximation. So anyway, that is pretty much the idea. And of course, later on, you guys can also use this for any other infinite series, but just you have to make sure that the series has to be converged first, and you can actually use the integral test for the series to see if it's convergent or divergent. Of course, we talk about convergent series. Make sure the function is positive, continuous, and decreasing so that the rectangle arguments will work. And before we go, as I promised it, I will tell you guys the answer to, so this is just a bonus. The sum as n goes from 1 to infinity, 1 over n to the 4th power. I pretty much look at 1 over n squared and just square that, huh? So let me tell you, if you look at the answer, pi squared, yes, we square that. This right here, yes, we get pi to the 4th power. And by now, I'm pretty sure a lot of you guys are guessing, hey, shall we just square the 6 and then we get 36 on the bottom? Yes. No, just kidding. We actually get pi to the 4th power over 90. Okay? So, in fact, when you have the 4th power right here in the denominator, you have the exact answer, pi to the 4th power over 90. The truth is, when we have the even powers in the denominator, the 2, 4, 6, and all that, you can actually come up with a really nice answer. But when you have a number besides 1, because 1 over n to the 1st power is actually a divergent, but 1 over n to the 3rd power, unfortunately, we don't have a nice exact answer for that. The sum as n goes from 1 to infinity, 1 over n to the 5th power, unfortunately, we don't have a nice exact answer for that neither, right? So that's pretty much the idea. And I will actually, I plan to show you guys this right here, and I will do this by the Fourier series, but I will do that during summer because right now I'm busy with all these calculus 2 materials for you guys and also for my students. Okay, so this right here is it. If you guys like my video, you guys can subscribe to my channel for more similar videos. Thank you guys so much for watching, and as always, that's it.